Let's talk about energy remoteness, which is the fact that we are separated from the things we want and need by barriers of energy, time, and complexity. As energy gets more costly, many things in our world will become more remote. So you've all probably heard that ocean water contains things like gold and uranium, but they're in such small quantities that it would take huge amounts of energy in order to process them to the high quality concentration that we would need. So energy is related to all kinds of things that we might want in the future. Think back to this milk example. Because we use thousands of units of energy to replace each unit of human labor to do modern tasks, the benefits in the form of wages, profits, or cheap stuff are very sensitive to the cost of the most important input into the production chain, which is energy. So this graph shows the profits under those three different milking technologies, and now for three different costs of energy. The no extra energy added example of manual milking, to be expected, would show no difference in profits from an increase in energy cost. Even the intermediate energy input shows only a small decline to wages and profits as electricity costs triple from 5 cents to 15 cents. But the high energy intensive technology undergoes a major impact. When electricity costs double from 5 cents to 10 cents, the blue to the orange, the profits shrink from $25 to less than $5. But more concerning is at 15 cents, a tripling of electricity prices. This fully automated energy milking technology not only doesn't show a profit, but has a steep $15 loss. So our global energy machinery and industry kind of all falls on a spectrum from intermediate to high energy intensity. Think airlines, cement manufacturing, aluminum smelting. These are things that use huge amounts of energy and are going to be very sensitive to energy price increases in the future. So this graph shows in the blue the amount of copper that was produced in the mining industry in the country of Chile over the last 15 years. Kind of flat to slightly higher. The red graph show the amount of energy required to get that amount of copper. Because the ore grades are going down, we need more and more energy to get a larger overburden amount of rock in order to get the same amount of copper. Now, when energy prices are cheap, we still make a lot of profits in this. But as energy gets more costly, we use more and more of it, and that impacts the price of energy and the price of copper and the price of everything else. Everything we do is going to become more expensive if we cannot reduce the energy consumption of specific processes faster than prices grow. Okay, so here's a long-term perspective of what percentage of our economies, of human economies, energy use was as a percentage of the cost of the total economy. So this is a 700-year chart of the United Kingdom. And over many hundreds of years, the power and food, which was physical labor inputs, were between 40 and almost 100% of the entire economy. And you can see the impact of fossil fuels here in the 1700s, 1800s, 1900s. The energy cost as a percentage of the size of our economy went way down. But now this hit its low point. It troughed in around 1999 and has been going up. Now we're around 7 or 8% of the percentage of our economies is energy cost. So when energy is very cheap, it allows for lots of other things to happen in an economy like Disneyland or NASCAR or universities or libraries or vacations or cool little gadgets. So the chart on the left, the pyramid on the left, shows that the energy finding, the energy extracting, and the energy refining and delivery of an economy is only 5%, leaving 95% of the energy to be spent on a variety of other things. If we're headed for a future when energy costs more and more of our resources are devoted to the energy sector, say 15% or even 20%, that implies that we're going to have to give up some of the other things. What might we have to give up as we allocate more and more of our energy and material resources to the energy sector, which is happening now. And this concept is especially important to agriculture. Cheap fossil energy allowed us to have only a very small percentage of our population working directly in energy and agriculture, currently around 3% in the United States, as opposed to a country like India where 70 to 80% of people are still working in agriculture. So we currently use around 10 to 12 fossil calories to grow, process, package, deliver, store, and cook 1 calorie that we eat. For most of our history, the agricultural system of humans was an energy source. We got more calories from the food than we put in from our muscle labor. But today, globally, it's a 10 to 14 to 1 sink, depending on how you account for food waste. How we manage this as fossil carbon gets more expensive is going to be a very important question. So we can now see that energy is central to our economies, and fossil energy underpins our industrial systems and their affordability. Well, how much fossil carbon is left? Or is that even the right question? We're going to take a look at energy depletion in the next video.